So we're going to cover today is how to kind of intuit, right? How to intuit what the charges are for the different groups, as well as rationalize when the R groups are either, or any group, not just the R groups, any group is protonated or deprotonated without having to memorize this, because this is easy to get mixed up, especially on a test under stress. All right. Before I get started, are there any kind of lingering questions from last Tuesday or any other content that I can answer within the next minute or two? All right, so we'll get started. So the way I like to rationalize this out, to determine whether a subgroup or a group in general is going to be deprotonated or protonated, and by extension, whether it has a negative or positive charge, is to imagine that we have this beaker. Let me draw a beaker real quick. And we have it filled up with some kind of fluid, let's say water. And for those of us that are joining us for the first time, these notes that I'm drawing out and writing out will be uploaded to the Discord channel right after our session. So don't worry about taking a lot of notes. Just actively listen. Be engaged, participate if you'd like, ask questions, and have a good time. All right, so let me fill this up with water. Should have made this beaker so big, been a little easier to fill up. Okay, all right. So what I want you guys to think about is we're going to put in this molecule cysteine, right? If you guys haven't got your amino acids down yet, please do. Tonight, okay, download this amino acid quiz app onto your smartphone. It's literally called Amino Acid Quiz. It's an easy way to master your 1-letter, your 3-letter, and your structures within a couple weeks, 1 or 2 weeks, just doing these kind of little mini quizzes, okay? And if you're in the 490s or low 500s, that could improve your score anywhere from 3 to 5 points right there. Now, we're going to add this cysteine into this beaker, and maybe I'll put C for the cysteine as a single substrate or single molecule. And what we're going to do is, well, first what we're going to do is we're going to define what pH is, and we're going to define what pKa is, right? And this seems kind of obscure for a lot of people. And actually what I'm going to do for simplicity is actually I'm going to define pH using the word pH, okay, or the symbols for pH. So that might be a little bit backwards. So pH is really, the way I want you to think about this is the, quote, pH of the solution, okay? Now I know most people don't like that. I'm typically not a fan of using the word in the definition either, but I think we inherently understand what kind of pH is, and I think here it's a fair pass. So it's the pH of the solution. Let's say in this case the water. And then pKa, the way I want you guys to think about this, the pKa is simply, quote, the pH of the substrate, So pH is the pH of the solution, pKa is the pH of the substrate, okay? And one of the ways we can rationalize this out is that they're both power logs, right? They both have this P for power, right? They measure the power of either the hydrogen concentration or the K, dissociation product over reactant, okay? And so these, let me write that out, are both power, they're both on the power scale, right, in red here. And so that's going to be really helpful for us. It's going to be very, very helpful for us. Because what we can do now, with that understanding, is we can put everything, pK and pH, is kind of on a pH scale. On a pH scale. And what we're going to look for is relative differences. Relative differences. And so the question asks us, what is the charge of cysteine at a pH of 6? Okay. Now, if you know the shortcut on the right-hand side, when pH is greater than pKa, things will be deprotonated. If pH is less than your pKa, it becomes protonated. If you know that, fantastic. But I don't want you guys to just memorize that. It's also important that you guys can just derive that or intuit that, make life a little bit easier. So if you're on the test and you're freaking out, okay, as could happen, you don't have to stress. You can kind of, grab some tools in your tool bag and kind of figure this out with the method I'm showing you. So our pH, we said the pH of the solution. Let me highlight that as well. So the pH of this solution in the question stem says it's 6 in this example. Fine. So what we're going to do now is we're going to put all these different values. Okay, we're going to put all these different values, and I guess maybe to make this a little bit easier, I'm going to put this down here as well so we can see what those values are. And we're going to put them all on a number line on a pH scale. Right? And a pH scale is just from 0 to 14. Or 1 to 14. However you want to do that, that's fine. Don't worry about it. Draw yourself a number line. And now what you're going to do is you're going to put all these values on that number line. So I like to start off with my pH, the pH of the solution. And we'll kind of approximate and say, okay, the pH is around 6. And then we're going to put in 3 of these pKa values throughout. So the pKa value, let's number these. We'll say 1, call this 1 over here on the right, the carboxylic acid group. The amine group, we'll call that 2. And actually, we'll do the cysteine group, the R group is 2 for order. And the last group, the amine group, is 3. Now, the MCAT, right, we'll expect you to kind of have a general understanding of what the pKa values are of the carboxylic acid group as well as the amine group. I would not stress too much about knowing the other pKa values for the other amino acids. Specifically, I wouldn't stress about knowing the R values, okay, pKa values for the R groups. It's too much. You're going to be given that information, okay? But hopefully this makes sense. When you look at the pKa of this carboxylic acid group, well, it's around 2, right? We say pKa is just the pH of the substrate. And so it makes sense that's around 2. And that's going to fluctuate depending on the amino acid that you have. Likewise, the amine group, you should know that it's going to be basic in nature. Well, pKa value of this amine group is around 10. So that makes sense. Bases, right? Things that are basic tend to be around 9 or 10 on the pH scale, or higher than 7 anyway. And so again, you don't need to do any mental gymnastics here. You already know this inherently, okay? So please, please, please don't waste your time trying to memorize every single pKa for each of the amino acids. There's no sense in that. So like I said, we're going to go ahead and throw these numbers, these pKa values, onto this pH scale as well. All these pKa's on the same pH scale. And so 1 is 1.96. Let's just call that 2. Make life a little bit easier. So 2 is over here. And this is going to be pKa 1. And what's next? Well, the R group, pKa 2, is, we're going to say that's 8, make our life easier. And then the last one is at 10, and that is pKa 3. Cool. So our reference, remember what I said up here, we can put all this stuff, pK and pH, on the same scale, the pH scale, and we're just looking for relative differences, okay? So no matter what concentration you have of substrate, what I want you to think about, let me rephrase it. So no matter how much cysteine we have, I want you guys to simplify this and think of it that we only ever have one. We only have one molecule that we're looking at, okay? So it doesn't matter if we've got 10 million molecules or a gazillion, just think of it, simplify, and think of it just as one. One substrate being added to this beaker in a sea of a certain pH, in this case, an acidic pH of 6. And we're looking at relative differences, okay? So if we were to think about pKa1, right, pKa1 right here, and we're to compare the relative difference between pKa1 and pH, we can see that, well, pKa is at 2 and pH is at 6, right? So relatively, this pKa, this group, is surrounded by a basic fluid, right? It's surrounded by base because that pH is at 6. It's more basic. It's surrounded by a basic environment, okay, by 4 orders. So if we have this R group on the cysteine, right, its relative pH is at 2, and it's surrounded by a basic environment. That means what? Well, that means relatively it would experience a lot of base around it. And what do bases do? Anybody? What does a base do?
Hydrogen acceptors?
Yeah, they're hydrogen acceptors, right? They're going to take hydrogens away from things, typically from an alpha carbon, right? But they're going to take hydrogens away from stuff because they want to get neutral. They're negatively charged, so they want a proton, right? That's typically positively charged to become neutral, to become stable, right? And so what's going to happen here is that this R group, this pKa1 on this cysteine, right? It experienced relatively a basic environment surrounding it, because the pH is more basic, right? It's shifted to the right of the 2, which is more basic. 6 is more basic than 2. And so it's going to become deprotonated. And when things become deprotonated, right, they're going to have a -1 charge. Well, how do we know that? Well, if we drew some OChem out, we can also rationalize this, right? So let's say we have a hypothetical structure. Maybe I'll put a carbonyl group in here since the MCAT loves carbonyl groups. And let's say this is my alpha carbon, and this, I guess either side could be, but maybe I'll put a little carbon on the other end as well, an extra one. And let's say we got all these alpha carbons right here. And a base, what it's going to do, it's going to come in and it's going to snatch up one of these hydrogens. It doesn't care about the electrons because it's already negative, right? It's negatively charged, doesn't want any more negative charge from the electrons. And so those electrons that were formerly between the hydrogen and the carbon are now going to be deposited onto this carbon. And in doing so, this carbon is going to become negatively charged in turn. So when things get deprotonated, they become negatively charged. That's one way we can rationalize that out. Okay, well, I think it's pretty obvious what we're going to see next. In comparison to the value of 8 and 10, right, we'd say 8 and 10 is more basic relative to this pH of 6. 6 is more acidic than 8 or 10. And so both these molecules, both these substrates, or these pKa values, these groups on cysteine, right, they're going to experience a relative pH environment that's acidic. And so they're going to see a lot of protons relative, H pluses. And so if that's the case, they're simply going to become protonated. And if things get protonated, well, it's going to be the exact opposite of the situation towards the left of the pH line. They're going to become charged by, they're going to have a +1 charge, +1. Okay. So again, put them all, treat this as being equal. Think of pKa and pH for simplicity as being the same thing. Don't overthink it. Okay. Put them on a number scale, on a pH scale, and just look for the relative differences between the pH, which is the pH of the environment that surrounds the substrate, in this case cysteine, and see whether relatively that pKa or that group sees a basic environment around it or an acidic environment around it, and then you can go from there. Okay. So intuitively, if you understand that, then you may be able to use a shortcut up here where you can memorize pH. When pH is greater than the pKa, it becomes deprotonated, right? Because the environment pH, which is the pH solution or the environment, is going to be more basic. If things are more basic, things are going to get deprotonated. If the pH is less than the pK, right, that means that the environment, the pH of the environment solution surrounding the substrate is more acidic. Well, that means it must become protonated. So I think it's good to memorize both ways, but I really want to make sure that you guys understand this intuitively, what is happening to these different pKa groups. So in this case, what is the net charge? What is the net charge? Going back to this question, let me recopy. We'll put it back down here. What is the net charge? And actually, let me change this. What is the net charge? Let me add the word net charge of cysteine at a pH of 6. Well, if we look at the charge count, well, we got one negative group, one minus for pKa1. For pKa2, we've got a +1. And for pKa3, we also have a +1. And the total charge is just going to be +1. Okay. So that is the answer. Okay, that's what we want. Maybe I'll use a green check mark to indicate that it's correct. So I think what we'll do is we'll do one more, and I'll probably call on people. I'll pick on you guys a little bit, so try to get involved a little bit. Okay, I know nobody likes to be called upon, but I appreciate it. And then what we're going to talk about is the isoelectric point. How to calculate the isoelectric point for certain amino acids, or how to go about that in general. Okay. So maybe what we'll do is I'll copy this question again, and instead of a pH of, and maybe I'll copy this amino acid cysteine as well, and instead of 6, maybe we'll change it to 9. Okay, we'll change it to 9. So what I want you guys to do on a scratch piece of paper, we're going to take a quick 5-minute intermission. Okay, I want you guys to go ahead and put these values, the pH and these 3 pKa values, onto the pH scale and go about the same exercise that you guys just saw. Okay, but this time the pH is at 9 instead of 6. Okay, maybe I'll zoom out just a little bit so you guys can see everything before. Okay. All right, so we'll come back in about 4 minutes. So you guys should be able to do this quite quickly. And in chat, in the voice chat, how about you guys just tell me what you guys think the charge will be? And if you guys do the pH scale, take a picture of it, okay? Send it my way. And the first 2 people that do that, I'll give a free hour of tutoring one-on-one. Okay. So we're just taking a quick intermission, a couple minutes, and we're doing this problem down here. All right, so looks like you guys are getting after it. In chat, I see a lot of -1s. Had an individual also direct message me. Nope, Andrew's on top of it. Send me a picture of the scale, maybe. Okay, good. Yeah, excellent. Perfect. I love that. Okay. So Andrew was able to shortcut this and say, oh, instead of drawing that picture with the bases and stuff, I just know it's going to be negative, negative, and positive. That works too. So let's do this together real quick. I'll do the long way, the colorful way. Okay. So, Andrew, explain this process to me if you would. Walk me through it. Let me be your pen, and you be my guide.
All right. So we write out the pKa's and the pH.
Okay, let me do that real quick. So the pH, right? That's going to be a reference line, and that is at, let's see here, I think it was around 9. Okay, yeah, 9. And okay, so then let me go ahead and put these pKs, and I guess it doesn't really matter which order they go in. I'm just going to number it. Okay, so we got 1 at 2, we got 1 at 8, and we got 1 at 10. Just for clarity, I'm going to put pKa1, pKa2, and pKa3. Is that fine?
Yep.
Okay, now what?
Okay, so so since the pH is greater than the pKa1
Okay.
at 2, it'll be quote unquote more base.
Yeah, so right, so because exactly right. So because 2 and 8 are both more acidic than 9, right? Remember, pK is kind of the pH of the substrate. That's another way to think about that, right? And the pH is the pH of the solution, the environment, right? It's surrounded. Both these pKa's are surrounded by a solution that is more basic than either at 2 or 8. So they're going to experience a lot of base. Relatively, right?
Right.
And so that's going to become deprotonated. And what's the charge whenever you deprotonate stuff?
Negative.
Yeah, -1. Fantastic. Okay, and if you can give a similar explanation with this relationship I discussed with relative changes in pH and how the pK would perceive that as, that'd be great.
Right. So the opposite way, which is since the pH is less, it'll be in more acidic condition. So you'll protonate it, and it'll be positive.
Good. And then the net, as I already said, right, is going to be, well, the net charge of this is going to be, well, we got pKa1 is going to be, well, that's going to be -1. pKa2, that's also going to be -1. And then pKa3, 3 is going to be +1, or a total of -1. So everybody did a good job on that. Okay, not too bad. Okay, so let's talk about how else you might see this question being asked on the MCAT, right? Because it could ask you about charge or net charge, but it may also just as easily show you 4 substrates, right, with different charges on them, right? So you may have this starting molecule, right? And it's going to ask you which of the following is the correct illustration of cysteine at this pH, right? And so they might give you the starting picture here, and you might be asked to identify what it would look like after it's been exposed to a pH of 9. Well, what do we know? Well, we know that both, right? We know that this group 2, and group 1 are going to be negatively charged based on what we just did. And we know that the third group here is going to be positively charged. So let's draw that out. So you'd have S minus, right? Because it's going to be negatively charged. And then this amine group is going to become an NH3 plus, right? Because we said it's going to be positively charged, it's going to get protonated. And this carboxyl group, this acetic acid, excuse me, it's not acetic acid, it's a carboxylic acid, misspoke, is going to be not OH, it's going to be O minus. Okay? So that's another way you might see the MCAT test you on this, right? It's the same idea, it just slightly tweaked. And if you do this, you can do both ways or both forms of this problem that you might be presented, or how it might be presented as on the MCAT. Okay, so this was kind of quick and easy, 30 minutes. I like that. So now we're going to kind of talk about how to calculate the isoelectric point. Okay, what can you guys tell me about the isoelectric point? What is the isoelectric point?
Whenever the total charge is 0.
Yeah, good, right? So the isoelectric point essentially is a point in the pH